Let's imagine solving a linear system like this one here using row operations. So, to do row operations, the first thing we'd have to do is, I guess maybe the nicest way to start would be interchanging these first two rows, or interchanging the first two equations. So switch row 1 and row 2. And, I mean, this is such a trivial operation, but still we're going to have to copy down the entire system of equations. Right now we have to write out x plus 2y minus 4z equals 23. And the other two equations, even though they aren't really changing, we still have to copy them down to sort of have a complete and valid copy of the entire system. Oh, this one right here, I intended this to be a z. And if you imagine doing all of the other row operations that we would need to do to solve this system, in fact, most of them don't change very much about the system. They just kind of change some of the numbers. In fact, often some rows don't change at all. So the next thing we would do is we would add multiples of the first row to the last two rows to zero out some of the x terms. And that's going to change some numbers, but they're still good. The first equation won't change at all, and in the last two equations, the y's and z's are all going to be in the same place. As for all of these row operations, where the x, y's, and z's are don't change. The only things that change are what all the coefficients are. So it actually would save us a lot of work if we just stopped writing down all of the x, y's, and z's, because they aren't really adding any information. We can just remember that they're there without actually writing them down. So let's back up and rewrite this system of equations, but we're only going to keep the information that we really need. So the coefficient on x is minus 4 in the first equation. The coefficient on y is 2. The coefficient on z is 1. And then the right-hand side of the first equation is minus 7. Okay. So from the first equation, this is all we really need to remember to know that the first equation was minus 4x plus 2y plus z equals negative 7. For the second equation, the only thing we need to write down are the coefficients. So x has a coefficient of 1, y has a coefficient of 2, z has a coefficient of minus 4, and then the right-hand side is a 23. And then for the third equation, it's minus 3, minus 2, minus 1, and minus 14. So just this grid of numbers represents everything we need to know what the original linear system was. Some people like to put a dotted line or a vertical line between the first three columns and the last column, just to remember that the columns on the left represent coefficients for variables, and the column on the right represents the right-hand side of the equation. Also, it's kind of strange to have all of these numbers kind of floating into space, and so usually, in fact always, we will put all of these numbers in some kind of brackets just to sort of keep them packaged up. So I'll use square brackets. Some people use giant parentheses instead of square brackets, but either is fine, as long as you sort of somehow indicate that all of these numbers are packaged together. So this collection of numbers, this grid of numbers, is called a matrix. And when a matrix represents a linear system and the right-hand side of the linear system is sort of tacked onto the end of the matrix, then this is called an augmented matrix. So this is the augmented matrix that represents the linear system that we started with. Now we can do row operations on the augmented matrix, just like we did row operations on the linear system, except we aren't going to have to write down all of the extra pluses, the x, y's, and z's, or the equals, because we know they're there, right? We know they're there, so there's no sense in writing them over and over again. We will only write the numbers because those are the things we have to keep track of, all the coefficients. So we can swap row 1 and row 2, just like we would have to begin with. So this gives us 1, 2, minus 4, and 23, and then minus 4, 2, 1, negative 7, negative 3, minus 2, minus 1, and minus 14, and so on, right? So given any augmented matrix that represents a system of linear equations, we can do the same elementary row operations that we did with systems of equations. We can interchange two rows, we can multiply a row by a constant, and we can add a multiple of one row to another row. And all of these row operations, when we perform these row operations on an augmented matrix, the solution set of the corresponding linear system won't change. Because when you do a row operation on an augmented matrix, the resulting augmented matrix is obviously the augmented matrix for the resulting linear system if you did the same row operation for the linear system itself. So the augmented matrix really keeps track of everything we need to solve a linear system. So with that in mind, let's go ahead and actually solve a system with an augmented matrix. So to start out with, we need to just write down the augmented matrix for this system. And this is just going to have the coefficients. So 1, 1, 3, and then the right-hand side is negative 6. And then when you have a missing variable, that just means the coefficient for that variable is 0. So for this second equation, it's 0, 1, 0 are our coefficients. And then the right-hand side is 2. And then for the last equation, 1, 3, 3, and the right-hand side is minus 4. And then again, to indicate that this last column is actually the right-hand side of a system of equations, we'll put this vertical bar here. And now we can do row operations. So let's see. We already have a 1 in the upper left-hand corner, so let's use that 1 to zero out everything below it. In the second row, we already have a 0 here, so we can, to zero out the bottom left, we can take row 3 and subtract row 1. So this doesn't change the first row, 1, 1, 3, minus 6. Doesn't change the second row, 0, 1, 0, 2. And then the third row, so remember third row is going to be third row minus first row. So 0, 2, 0, so third row minus, so plus 2, like this. Okay. Now that we've zeroed out everything below this upper left-hand corner, now we can move down a row and zero out everything below this 1. So we're going to take row 3 and subtract 2 times row 1. So this gives us 1, 1, 3, minus 6, 0, 1, 0, 2, and then, so third row is now third row minus 2 times second row, so 0, 0, 0, minus 2. Okay. Now that we have sort of along every column, we've zeroed out everything below this leading 1. Now we can think about the linear system that this represents and see what its collection of solutions would be. Well, this last equation says that 0 times x plus, or sorry, this last row represents an equation that says 0 times x plus 0 times y plus 0 times z equals negative 2, and this clearly has no solutions. So this linear system has no solutions. You can see that not having to write down the x, y, z's, pluses, and equals all over the place actually saves a fair amount of writing. So from now on, whenever we need to solve a linear system of equations, we'll write down its augmented matrix and solve and do row operations to do the same row operations on the augmented matrix that we would have done to solve the linear system.